Note number 3, we know that this is the circulation. So this is more big picture stuff now. So this is just a restatement of Stokes' theorem. C is, as long as it satisfies the original theorem, we're happy here. S doesn't have to be super small anymore. So what Stokes' theorem says is the circulation of F around P, around C rather. Again, the assumption is that C is a closed curve. Okay, so how could we interpret the right-hand side? It's the sum. We think it's a limit of a sum. A double integral is a limit of a sum, right? But we think of it as a sum of, well, hold on. Let me do this. Well, yeah, so we know that this piece gives us the circulation, right? So remember what curl of F dotted with n is. It's the circulation per unit area, right? But you multiply it times ds, the area part goes away. So that piece, curl of F dotted with n ds, measures the curling around a point-wise, right? So let's say, let's say it this way, curling around, for any particular point, it's the curling around a point on S. And then what does the entire integral do? It adds all of them up, right? It adds up all the curling on the surface of S. So I'll say it this way. It sums up the integral, everything on this right-hand side sums up all the curling of F around points on S. And then Stokes' theorem says these two things are equal. So think of the circulation around points. So think of that back to that small picture. Think of circulation around points on S. What this is saying basically is that a lot of the curling around individual points on S cancel out. They cancel each other out. If you were to draw a picture, I wasn't going to do this right now, but I got going on it, so I will. So if you were going to draw a picture, let's say, like the pillow picture I often draw, and you break it up into a grid of, these are curvy linear curves that lie on S. So the pillow is S. And if you look at individual points here, so individual points here, C is comprised of all of these. So if this is C1, this is C2, this is C3 on the outside, C4, then C is the union of all of those. Then what happens is you've got the vector field F kind of swirling around this point, right? But if you want to think of it in terms of the left-hand side, the line integral side, you can individually think of the curling, since this is a super small surface patch of F, you can think of the curling as the circulation around this point that I've indicated here. And notice how I oriented that little boundary of that subpatch. As you look down on it, assuming that the normal vector points in an upward fashion, where k component's positive at least, then it's oriented positively, right? So what's going to happen is that if you look at a similar picture to an adjacent patch, and you orient that in the way you're supposed to, counterclockwise, let me go to 200 magnification. Okay. Then do you see how it's going to be oriented in the opposite direction on the side they share? Do you see how it's going to be oriented in the opposite direction on this side that they share? So that the circulation cancels on that side. And on any shared side on the interior of that grid, not on C1, C2, C3, or C4, but on the interior of that grid, any shared side, you're going to get that kind of cancellation on the inside, which is why the circulation really only matters around the main curve on the outside, comprised of C1, C2, and C3, and C4. So basically, this relationship, although it still blows my mind, if you think of it in those terms, it's almost believable, right? So we're just saying, oh, okay, so this guy here sums up all the curling of F around points on S, and there's going to be a lot of cancellation there, and that's going to be equal to the circulation of F around the main curve C because of that cancellation. Does that make any sense? A little bit? We're going for a little hand-wavy argument here. And I think that at least helps you wrap your mind around what this is saying and why it might be true, although it's still crazy that it works. Note number 4, if the curl of F equals 0 throughout the domain of F, then we call F irrotational. Does that make sense? This curl kind of measures rotation, circulation. If that equals 0, we say it's irrotational. And of course, it's conservative. I just wanted to mention that there to remind you. Note number 5, for a given boundary C of S, the double integral, or let's call it the surface integral, of the curl of F dot n ds, that's the right-hand side of Stokes' theorem, right, is independent of the surface. What? So here's what I'm saying. Let's say you have your boundary curve. Maybe it looks, so this is your rim of your surface. Maybe it looks like that. Call it C. And I'll even make a copy of it so it's exactly the same. But let's say, for the sake of argument, that in this, for our first surface, we'll call it S1. We just make it the flat plane segment. By the way, it can be a flat plane segment if the curve is flat, but the curve doesn't have to be flat. Okay, that's just the way I'm drawing it. So let's say we let S be this flat surface here. So let's call this surface in red S1. And then let's say S1 gets warped into S2 some hill. What we're really saying then, as long as that's the same C, we're really saying that the surface integral over S1 of the curl of F dot n ds, that's S1 right there, is equal to the similar integral but over S2, curl of F dot n ds. Now, why do I know this? Because they're both equal to the left-hand side of Stokes' theorem, right? The line integral over that curve C of the vector field. So it has to be true. So those two surface integrals are independent of surface.